Hello, this is the final presentation for the optimization of a home water filtration system. This is Team 4 with Hongkai Chen, Griffin Coolidge, Aubrey Kleinsorgi, Kana Moriyama, and Josiah Wong. The system is intended to be placed in a standard house, accepting mainline room temperature tap water as the input. The system consists of a reverse osmosis module, storage unit, and post-carbon filter, which work together to provide an output of chilled and filtered drinking water to the residents of the home. The first subsystem, the reverse osmosis module, consists of a pre-RO filter, an RO filter, and pump. Different materials can be chosen for these three components, which affect the water flow rate provided to the next subsystem. The second subsystem is the tank storage unit, which can be designed with varying height, inner radius, material thickness, insulation thickness, metal cap thickness, and insulation cap thickness. These design choices, along with the flow rate coming from the first subsystem, determine the flow rate going to the last subsystem. The last subsystem is the post-carbon filter, in which we can choose the length, diameter, and average particle size of the activated charcoal. These choices, along with the flow rate coming from the previous subsystem, determine the outgoing water flow rate. Designs of all three subsystems affect the purchase price and maintenance costs for the system throughout its life cycle. The flow rate Q is the coupling between our subsystems, as subsystems 2 and 3 receive water at rates outputted by the prior subsystem. No linking variables are present. The goal of the system-level design is to minimize the average cost to the homeowner over the system's life cycle. Optimization at the system level is necessary because minimum costs can be found for each subsystem, but adequate supply of filtered water must be provided by the overall system. Higher flow rates provided by the reverse osmosis allow us to design a smaller tank, while a larger tank allows us to filter water at a slower rate.
Our model has several parameters, most of which define physical quantities, such as the water demand on our system and the density of water, while others define the unit costs of materials and electricity. We have 11 design variables. Variables 1 through 10 are local variables that belong to specific subsystems, while variable 11 is a shared variable, Q tilde. This is an auxiliary variable for our coupling variable Q, which is a volumetric water flow. Q tilde is used in 3 of our intermediate variables. One to find the velocity water is moving through subsystem 3, as well as the empty bed contact time of subsystem 3. The last one uses Q tilde and our water demand variable Q hat to define a target inner volume for our tank. Our objective is to minimize the total cost of our system. The cost of subsystem 1 is the annualized cost of materials for the filter and the pump. The total cost of subsystem 2 is the cost of material to build the tank, as well as the operational cost of refrigeration. And the cost of subsystem 3 is the cost of the carbon used, the housing, and electrical components. Our inequality constraints for our subsystem is that the inner volume of our tank has to be greater than or equal to our target volume. We enforce a water cleanliness target, as well as a maximum Reynolds number to ensure laminar flow. Because we use IDF modeling, we enforce that Q tilde has to equal to Q, where Q is the volumetric flow calculated in subsystem 1. Our system has to be able to fill 5 cups of water within a minute. There are different ways to achieve this, such as increasing the tank storage size or increasing the water flow from subsystem 1 by either choosing a more efficient reverse osmosis filter or a stronger pump. However, all of those increase the total cost of our system.
Our objective function is purely analytical, and the cost term is computed directly from the equations at each iteration. This means that there's no simulation or surrogate approximation involved. The assumptions are that there's steady state flow throughout, laminar flow in the carbon filter, constant bed porosity, water exchange at a constant daily rate, and an ambient temperature fixed at 300 Kelvin. The constraints shown reflect both physical and performance requirements. Equality constraint Q tilde minus Q equals 0 is the IDF coupling condition. This is what ties subsystem 1's output to the rest of the system. The tank volume constraints and the absorption decay constraint enforce that the system actually delivers usable drinking water. The flow differential function shown is a physical heart of the tank size and logic. Q hat is our benchmark demand and represents the flow needed to fill 5 glasses of water within 1 minute. The inner tank volume must be large enough to accommodate the gap between what the RO system slowly produces and what the user demands quickly. This creates a direct trade-off between subsystems. If subsystem 1 selects a more powerful pump and produces a higher flow rate Q, the required tank volume in subsystem 2 decreases because there's less need for buffer. This also works vice versa. The optimizer resolves this trade-off automatically by treating Q tilde as a shared design variable both across subsystems. Each cycle begins with the current design variables being processed through the objective function to compute total cost. Simultaneously independently, the constraint function evaluates all 5 conditions at that point. fmincon may visit infeasible points during the search, but the equality constraint Q tilde minus Q is only driven to 0 at convergence and not forced at every step. Convergence will occur when the KKT optimality conditions and constraint violations both fall between 1e-6 or when 3000 function evaluations have been run. We chose IDF with fmincon because our problem is continuous, nonlinear, and well characterized by physics-based equations. This made gradient-based optimization appropriate. The for function inside our objective handles discrete components that require integer values, so this is also helpful to attaining our result. As mentioned before, balancing V in with a linking variable Q was really the main challenge we had to face, so using this IDF with the coupling variable allowed us to find the solution that we were looking for. Handling this uncertainty with the Q hat benchmark ended up yielding a valuable output, and we saw a significant increase in our optimality when we combine these systems using this algorithm.
These are the system optimization results. Only the first 3 states' initial conditions were changed because it was shown in our testing that the other initial conditions had little to no effect. To changing of these first 3 states, we could see that F star varies greatly. This is because these initial conditions relate to the first subsystem, which depend on integer value choices. The solver, depending on the initial condition, is getting stuck in local minima and not traversing to the other global minimums. Regardless, an F star of $141.70 was the best trial, as shown. Moving on to constraint sensitivity, we took our 4 constraints and perturbed using an alpha of 10%. The only sensitive constraint was the inner tank volume constraint with a sensitivity coefficient of 1.25. Moving on to parameter sensitivity analysis, we had many parameters but chose these 3 because of how they interacted with the rest of the system. For example, house water pressure was the only parameter relating to the first subsystem, so we thought there was a high probability for it to have high sensitivity. The inner radius of tank and height of tank are terms that are raised to the power in our equations, so we also thought they would have high sensitivity. Again, an alpha of 10% was used, and the sensitivity coefficients are shown. The most sensitive parameter is the inner radius of the tank.
For the reality check, we compared each optimized subsystem with similar commercial products. For the RO module, our optimized cost is lower than comparable retail RO systems because our model only includes subsystem level costs. For the storage unit, the optimized size is realistic, but the predicted cost is lower than the market price because the full manufacturing and certification are not included. For the post-carbon filter, the optimized cost is in the same order of magnitude as commercial inline filters, although the model appears slightly conservative. For the subsystem-to-system comparison, the main takeaway is that the full system optima is not simply the sum of the three subsystems optima. Once the subsystems are optimized together, coupling constraints reduce the design freedom. So the final design combines the compromise across RO production, storage, and final punishing. This shows the subsystem only optimization tend to be too optimistic. Finally, this project is ultimately a coupled household water filtration problem. The RO module is the main system driver because flow demand affects both storage unit and post-carbon filter. In the future work, the RO model can be improved with for manufacturer performance data, and the storage and the post-carbon model can be made more realistic by matching commercial product more directly. And the full system can be solved as a one fully coupled optimization problem. Overall, our subsystem models are realistic, but the full design problem is strongly coupled, which is why the system level optimization is essential for producing a practical and commercially meaningful final design.